Hello, and welcome to the latest installment of the Aras Innovator demo series. Today we're going to see Aras Innovator connecting simulation to the digital thread. The demo series runs for 30 minutes and features all demo with no sales pitch. Each installment showcases a different capability of the Aras platform. During the webinar, everyone is on global mute. If you have any questions, please submit them in the questions panel within GoToWebinar, and we'll answer as many as possible in our Q&A session at the end. The demo is being recorded today, and when the recording is available, you'll receive an email with the link so you can share it with your colleagues or review it again for reference. We have on the line today Tim Keir, Director of Customer Solutions at Aras. Tim, take it away.
Thank you, Nicole. Hello, everyone. My name is Tim Keir, Director Customer Solutions at Aras Corporation, and today I'm going to show how the Aras platform can be used for simulation management. So this is the third demo series webinar about simulation management, and you'll see that we're continually expanding our capabilities in this area. The first webinar, this time last year, took place soon after Aras had acquired Comet Solutions, who developed software for simulation process management. Comet templates allowed users to capture simulation processes, to embed expertise and rules, and to make these templates available for reuse by others. That was powerful simulation process management, but simulations were still generally performed in isolation, as Comet lacked a connection to the digital thread. If physical testing of prototypes found issues, it wasn't easy to determine what simulation had been performed on the virtual equivalent of the design. So in the second webinar in May, I showed how simulations could now be created, launched, and managed from inside the Aras platform, and how Aras could create a digital thread to ensure that product development teams could easily track what simulation was performed on which version of the design, what results were obtained, who reviewed and approved the results, and where the results could be found. So this approach significantly increases the value of simulation, as teams now have access to the full history of simulation performed on their products. So now in the third webinar, I'm going to present a much richer environment for product development teams to perform and manage simulations. I'm going to demonstrate how the Aras platform can be used to create, launch, and manage simulations. The user defines what changes should be made to the design and what changes should be made to the environment that's to be applied to the design. And then Aras takes over, communicating with CAD tools, with system modeling tools, with finite element meshing tools, with solver tools, and post-processors. And Aras runs all the simulations and then produces a report. Now that's fairly similar to what I showed in the last demo series back in May, running simulations from inside Aras, but there are three new enhancements that I want to highlight today. Firstly is tracking trees of simulations and of designs. In simulation land, you hardly ever go from simulation 1 to simulation 2 to simulation to 3 to 4. You go from 1 to 1A to 1B. You know, I've created simulations like 1B final, which you can guarantee means you'll need to have another one. So it's important that you track your simulations, understand the decision process that made you go from this simulation to that simulation. What were the differences in the inputs? What were the differences in the outputs? Why did I make those changes? So with a tree of simulations and designs, you know, we can track that from inside Aras. The second enhancement I want to highlight is chaining simulations together, where we take the results from one simulation and use them as inputs in another simulation. The demo I'm going to show today shows a vehicle hitting a curb, and we run a first simulation, a system model of the curb collision, and we take the forces, the suspension forces, out of that simulation and automatically send them to a stress analysis of the lower control arm. So we've got automatic chaining of simulations now. And then the third enhancement I want to show is connecting simulation to requirements engineering. Requirements engineering is a fundamental aspect of lifecycle management, and for the first time we can now connect requirements engineering to simulations. So whenever you run a simulation, you can immediately see, does this version of the design meet its requirements or not? One other thing, I mentioned the use case earlier where a user sets the variables. I'm not just talking about simulation experts. An expert will certainly benefit from using Aras to manage simulations, but working inside Aras, a design engineer now has the ability to perform simulations too, and entire project teams can track the results of simulations and the status of designs. And before I finish this introduction, I'd just like to acknowledge the contribution of Inenzia, an Aras partner who've contributed a lot to the work I'll show today. So let's jump into the demo. Here we are in Aras Innovator. Let's talk about what you need to perform a simulation. We at Aras believe there are 4 main ingredients you need to create and define a simulation. You need a design. What is the representation of the product that we're going to analyze? You need an environment, a description of the loads and boundary conditions to be applied. You need a set of simulation instructions. How should the simulation be performed? And importantly, you need a set of requirements to allow an assessment of performance of the design. So in today's demo, we're going to review a series of simulations performed on a small passenger car. I've run some of the simulations already, and we'll look at them and their results, and then I'll create, launch, and review a new simulation live during the webinar. So here is the use case we're going to look at today. It is a passenger car in a curb collision, and the problem is, will the vehicle damage be acceptable? I'll just let it run through once more. Great. So that's what we're going to consider today. Let's go back to Aras and let's look at our requirements. Should always start with requirements, requirements engineering, requirements document. A requirements document is a collection of requirements. We have 3 requirements. Let's look at the first one. During this particular use case, so a collision with a 200 millimeter curb at 20 meters per second and 28 degrees, the maximum force at one of the suspension mounting locations must be less than or equal to 100 kilonewtons. We have another requirement which is similar at a different suspension mounting location. We've got to have a maximum instantaneous force of 20,000 newtons. That might sound like a lot of force, but this is just for a millisecond or so. And then the third requirement is for the control arm itself. In the same load case, we want our maximum stress to be less than 300 megapascals. That's a very high value, but the requirement here is that the control arm should not break. Plastic damage would be acceptable. Now, of course, a real vehicle or a real product has many sets of requirements. This is a gross simplification, but everything I'm going to show today with this minimal set of requirements and just a few simulations is scalable inside Aras for something as complicated as a full vehicle development program. So those are the requirements that we're looking at today. If I bounce back to PowerPoint again, a vehicle hitting a curb. So in order to assess the performance of our design against requirements, we need to run 2 types of simulations. First, we're going to run a full vehicle dynamics model. This is what you're looking at here, to calculate forces in the suspension components. And then we're going to do a component stress analysis to calculate the stresses in the lower control arm. Now, for the vehicle dynamics model, we're using a Modelica system model created by Modelon using the Modelon impact tool, which has been exported as an FMU, a functional mock-up unit. And the FMU contains definitions of all the variables and all the equations used by the model, and it can be run in isolation. So I don't have Modelon impact on my laptop, so I'm just going to show some pictures. And that's an interesting point. I don't need to have many of the tools that I'm going to use today on my laptop. Some of them I do, some of them I don't. I can set up Aras so that all I need on my laptop is a browser with everything else running on one or more remote servers. So here are some screenshots of the system model. Here's an overview. We've got a vehicle representation, a driver, operating conditions. Here is the chassis subsystem. Here is the front suspension subsystem. And if we go down even further, here's our system representation of the front left linkage. And one of the components represented here by this sideways A is the lower control arm. Now the user, when running this system model, has full control of the geometry of the different suspension components. So these are some of the inputs that we can vary to change the design of the suspension. And I've imported the FMU, the functional mockup unit representation of this system into Aras, and I've already run it a few times, making various changes. In particular, I moved the suspension hardpoints, as these have a big effect on suspension loads. And I've set up Aras to extract the forces and moments at the suspension attachment locations, and then apply those loads into a finite element stress analysis of the lower control arm. So back to Aras Innovator. We've used our product engineering application, and I've created a representation of our lower control arm. So here's the part, TC front lower control arm. I can see I have a CAD document attached to it. If I open up this CAD document, here we go. Just take a moment to open it up. This is a SolidWorks model. I can see that I've got a parametric design representation of my lower control arm. And some of the changes that I can make to this, either inside SolidWorks, which is what I'll do now, or inside Aras Innovator and having Aras communicate with SolidWorks, the sorts of changes I can make is I can move the suspension locations, I can change the thickness, I can change these angles to bring this section forwards. So let's just show one of those changes inside SolidWorks. So manage equations. This is a fairly big change, but if I change the X location of the rear inboard attachment location from 318 to 368, when I hit enter, it will automatically rebuild, and you'll see this mount location jump to the left. So that's the sort of change you can make live inside SolidWorks. And as I said a moment ago, we have a connector between Aras and SolidWorks. That means when I define inside Aras that I want to make this change, the change will get sent off and the CAD will be rebuilt. So I've just described connections to two tools, Model on Impact, from which I imported the system model, and SolidWorks. And we're going to use connectors to other tools during the stress analysis of the lower control arm. We're going to connect to ANSWER, which we'll use to create a finite element mesh. We will connect to MSC Nastran, which we'll use to calculate the stresses in the lower control arm under the application of the loads from the system model. And then we'll use VCalab to create a smart report, a lightweight, viewable representation of the simulation results. And these are just a few of the many simulation-related tools that Aras can connect to. And we are vendor and tool agnostic, which means we don't prefer or put limits on the tools that can be used during the simulation process. So here we are again in Aras Innovator. This is version 12 with its new and improved user interface. Let's just close a few windows. I understand in the next service pack you can close multiple windows, multiple tabs much more easily. But I'm a real fan of Aras Innovator 12. So today I'm going to show how the user can use Aras to create, launch, and manage simulations. The user defines the values of the design variables they want to use, and then Aras takes over. It'll run the system model of the vehicle curb collision. It will extract the forces. It will then communicate with SolidWorks to build the new geometry. It will create a finite element mesh, run a stress analysis using the forces, post-process, and report. And this is similar to the sort of thing I showed back in May, but the enhancements that I'm going to highlight today are tracking trees of simulations and of designs, chaining simulations, connecting one simulation, the curb collision, to another simulation, the stress analysis of the lower control arm, and then connecting simulations to requirements, allowing a better and quicker assessment of the results of each simulation. So let's have a look at our design that we're using in our simulation. This is our baseline lower control arm design. I can see that it has a design representation. That's the part that I looked at earlier, the TC front lower control arm, and it also has a series of design variables. These are the variables that we can change inside the design. They will change the system model to move the suspension hard points around, and they will also change the CAD model, the SolidWorks model that I showed a moment ago, and move those points around as well, and change the thickness and the section height and so on. So we need to be able to make changes to these design variables and then track those changes. And as I said a moment ago, that's generally not going to be a linear process. So we've implemented the concept of trees of designs to track our designs. So let's go back to our baseline design. Let's go into graph view. Here we're using graph navigation, a fairly recent addition to the Aras platform. Very powerful. Let me just expand some of these nodes. Here are a tree of designs that I've analyzed. I started with a baseline design. I then created a variant, design 1. I then created 4 variants, 1.1, 1.2, 1.3, 1.4, and then I created a design variant from 1.4. So I can use this tree to review what I did or what my colleagues did. I can add notes to explain the decision process. And so this gives a very rich view of the work that has been performed. And we have something very similar for simulations as well. That was for a design. But if I look at simulations, here is my simulation, my curb collision simulation. Let's expand some of these nodes. Now for the curb collision, I've just run 2 simulations. I ran a baseline and I ran a simulation where I moved one of the suspension hard points rearwards by 50 millimeters. So let's look at the baseline simulation. Here it's using the baseline design, baseline environment, baseline simulation instructions. If I look at my simulation results, let's start off by looking at the results for which I have requirements. I can see that my R0CL2, that's one particular mount location, its maximum force is 11 kilonewtons. Yep, that's less than, or that meets our requirement, good. But one of the other points, R0CL1, I see, our maximum force is 101 kilonewtons, which does not meet our requirement. And I can see that immediately just by coming into the results. So go back to our graph view. I then ran a different simulation, 5.1, where I changed the suspension mount location, moved it rearwards by 50 millimeters. Now, when I look at my results, I see first force, yep, that meets its requirement. Second force, yep, that meets its requirement, great. And the other results I have are the X, Y, Z forces and moments at the various suspension mounting locations. And these are what we're going to use, what we're going to send to the stress analysis of the lower control arm. So let's now go look at some of the lower control arm stress analyses. I started off with simulation 6. That was the baseline design, default loads, 1, 2, 3 newtons just applied at the locations. Here's simulation 6.2. I can see that it used the design where I've moved the suspension mount point rearwards by 50 millimeters. It used the loads from the curb collision with the equivalent change. So, let's have a look in more detail at this simulation. I can look at my design variables and see, oh, yep, here's the design variable that was changed. This is the X location of point R0CL2. I can see it was changed from 318 to 368 millimeters. The reason for the change is manual. You'll see in a moment it can be done automatically. And then when I look at my predecessor simulation, I can see that for this stress analysis, I was taking the loads from a predecessor simulation. This is the simulation 5.1. That's the curb collision. So I don't have to manually go and get the results from one simulation and copy them over and apply them to the new simulation. Aras is taking care of this. If I look at my environment variables, these are the forces that are actually going to be applied to the control arm. I can see instead of being 1, 2, 3 newtons, which is the original values, the values have now been updated to the values from the other predecessor simulation. And here I have reason for change, predecessor. So I can track what values have changed in my simulation from a design point of view and an environment point of view. And I can see the reason for the changes. Was it a manual user change, or was it done when I specified a predecessor? I'm sure this looks powerful. It may look a little confusing as well, but I'll show you in a moment that when you actually do this, it's really easy. So while we're talking about this simulation 6.2, let's have a look at some results. Maximum stress was 350 megapascals. That doesn't meet our requirement. Let's look at some simulation results. This is a smart report created using VCalab, and we can see here's the finite element mesh that was created automatically by our automation process, reaction forces, displacements, and here are our maximum stresses. And the hotspot, that 350 megapascal stress, is right here, close to the front mount location. So we're going to make some changes to the model in a moment, and I'm going to increase this angle and this angle too, to bring the section forwards to give it more depth, more moment, capacity, and hopefully the stresses will come down. So that's simulation I've done previously. Let's create a new simulation. I'm going to start with 6.2.1, this simulation. I open it up and let's see. Previously, some changes that were made were I moved the suspension point, I changed the thickness, but despite making those changes, my maximum stress was still too high. 336, a little lower, but it was still too high. So let's run a new simulation based on this simulation. So first thing is I've got an action here, create a child. Takes a few seconds. Okay, child has been created. If I go back to my list of simulations, refresh the search, I've just created 6.2.1.5. So let's open this simulation and let's make some changes to it. Firstly, you need to document what I've done. Change section angles. I need to change some design variables. Previous experience suggests the sorts of things I might want to change are to change this angle from 10 to 15 degrees. I want to change this angle from 15 to 20, and hopefully this will reduce the stresses. I want to keep everything else the same. I could change my environment variables. I could use a predecessor simulation, but I'm happy with the predecessor simulation I've got already. Now, when I save this design, when I save the simulation, I need to create a new design because I've changed some variables. So the design I'm simulating is now going to be updated differently inside SolidWorks. So Aras is able to take care of that. So look at this. We've got design 1.1. When I save this model with the changes to the design variables, Aras is smart enough to realize that we've changed the design, we've changed the design variables, therefore we need to create a new representation, a new design to carry everything we've done. So we've gone from design 1.1 to 1.113. The user doesn't have to worry about creating those nodes in the tree of designs. Aras does it automatically when you make changes. So I'm happy to run with these changes. So I'm done with my changes, and now I launch the simulation. It's going to take 3 or 4 minutes to run, and we may not have time to view the results, but if we do, I'll come back and we'll look at the results. So while it's running, just a reminder of what's going on in the background. This is a view of the process that is being run automatically behind the scenes in the simulation engine. I covered this in detail in previous webinars, but the key things to see here are inputs. Here's our CAD, outputs, VCalab reports, displacement and stress fields, and then the tasks. Update the CAD, run answer to create a mesh, run Nastran to do a stress analysis, run VCalab to get a smart report. And when the automation template is set up, the user can embed their rules and expertise to make sure that the meshing, the simulation, and the reporting are performed exactly how they want them. This process needs to be created by a simulation expert, but once it's been created and made available inside Aras, it can be used by engineers who are not simulation experts. So we're taking the previous domain that was specialized and making it available with appropriate guide rails to a broader audience inside the design community. So while we continue to wait, let's go back to our simulations, and I actually ran a an identical simulation earlier today, just in case this one didn't finish in time. I forgot to update the title, but this does have the design variables where I changed my angles as well as the previous suspension location and thickness. So if we look at the results of this simulation, we see, oh, excellent. Our stress is now 293 megapascals. It meets its requirement. Good news. I can look at the results file, VCalab, and see, I'll jump straight to the stresses. Look at the stresses. Yeah, the hot spot is still in the same place, but it's reduced in magnitude, which is good news. If I had more time, I would now show how I can send this simulation off for review so that somebody else can review the simulation and approve it. Don't have time for that. We're running out of time for the webinar. But what I'd stress here is that simulation, just like any other application inside the Aras platform, can be an integral part of the management of the product lifecycle. So life cycles, workflows, permissions, and so on. And you, the user, have the flexibility to set up workflows and life cycles in the way you want. And remember that as you configure Aras Innovator, you don't have to worry about future upgrades, as we, Aras, guarantee that we will take responsibility for upgrading our subscribers to new versions of Innovator. So just about at the end of the webinar, in summary, what I've shown is, Aras Innovator can support simulation management. As was the case back in May, we can define, launch, and manage simulations from inside Aras. Tasks can have the appropriate rules embedded based on guidelines and experience of the expert users. And we can use the digital thread to track details of all simulations. We can know who performed a simulation, on which version of the design, what the principal results were, and who reviewed and approved the simulation. But since May, we've added many enhancements. The three ones I want to highlight are trees of designs. We can now review trees of designs, trees of simulations, and this reflects the way in which most sandbox simulation is performed. This is not aimed at doing the one simulation to confirm that the release design is good. This is used to perform tens or hundreds of simulations to explore the design space. The more simulations you do, the more designs you can simulate and assess, the better the chances you're going to get a good design when you're finished. I also showed how we can now chain simulations together. The results from the curb collision system model will automatically apply the forces and moments to the stress analysis of the lower control arm. And we've connected simulation to another Aras application, requirements engineering. So after every simulation, we can immediately see if our design does or does not meet its requirements. So with access to simulation from inside Aras, simulation experts and product engineers can now deliver better and more timely requirements-driven simulation coverage. They can stay in sync with designs and variant changes. They can rapidly conduct analysis on product variations, options, and concepts, and they can automate repeatable simulation processes. And simulation can now be part of the digital thread, connecting information from concept engineering, detailed design, test, and production, from requirements all the way through the entire life cycle. Okay, that concludes today's demonstration. Nicole, do we have any questions?
Hi, Tim. Thank you. Yes, I know we're over time, but we do have a bunch of questions. So if everyone would like to stay on, we'll get through some of those. Is there a connector between Aras and Creo?
There is, yes. I only showed SolidWorks today, but we do have two connectors. I believe there's a CAD connector for importing Creo into Aras Innovator. And then we have a simulation connector as well for updating geometry and creating finite element meshes using ANSYS or other tools. For a full list of connectors, go to www.aras.com, search for simulation management. You should find the Aras Comet page, and it lists all the connectors, and Creo is on that list, yes.
Which SolidWorks connector was used in this demo?
Both of them. We have two SolidWorks connectors. We have a CAD connector that imports the CAD into Aras and builds the BOM. I only had a single part, but if I had an assembly, our CAD connector would import the SolidWorks assembly and build the part structure and the BOM inside Aras Innovator. So that was used. And then secondly, we have a CAE connector that connects to our simulation engine, and the simulation engine communicates with SolidWorks to update design, re-import it. And so I used both flavors of SolidWorks connector in today's demo.
All right, this is the last connector question that we're going to take. Are there connectors for simulation applications like STAR CCM and Abacus?
Abacus, yes, we have a connector for Abacus. STAR CCM, we do not currently have a connector. We are always collecting feedback for connectors that we would like to support. So I'll take note of that. Having created connectors to so many different tools, it's getting easier and easier to create the new ones. So thanks for the question. No STAR CCM yet.
Can you run the simulation to let simulation change the variable to achieve load requirements?
So I think that means optimization. Can you have, rather than have the user make the change, let an optimization algorithm run a simulation, look at the results, and then make changes. We don't have optimization inside this solution. What we do have is the ability to use third-party tools to run simulations using our simulation engine. So we have previous examples where we've used HEEDS, EyeSight, or Mode Frontier to run these simulations automatically and come to an optimal solution. So just as Aras doesn't have meshing tools, Aras doesn't have CAD tools, Aras doesn't have simulation tools, we connect to other tools, SolidWorks, ANSYS, Nastran, Abacus, ANSYS, and so on. In the same way, we don't have our own optimization tool, but we can connect to third-party commercial tools.
All right, I'm only going to take two more questions here. One is, do I need licenses?
If you mean, do you need licenses for your tools, Nastran, ANSYS, SolidWorks? Yes, you do. Do you need licenses to run the simulation applications? Yes. This is simulation management, or the simulation capabilities that I've showed today are available to subscribers, and to run the the simulation engine in the background, yes, you need licenses to that. That's available to subscribers. You need a little bit of training to use the simulation engine, the automation engine. It's hard to use out of the box, but if you're a subscriber and you want access to this, call us. We'd love to work with you.
All right, and the last question here that I'm going to take for today, can I run simulations on my HPC cluster or a public cloud like Amazon Web Services or Azure?
Yes, absolutely. As I said, I think towards the beginning of the simulation, beginning of the demo, I could set this up so all I have on my laptop or workstation is a browser, and I could connect to server number 1 running Aras Innovator, and I could connect to server number 2 running the simulation automation engine, and I could connect to server number 3 running Nastran, Abacus, ANSYS, LS Dyna, whatever, in the cloud. So any combination of local, in-premises, cloud, you can pick and mix and run where it's most effective to run.
All right, thank you, Tim. Thank you for everyone who's on the line today. And I apologize for any questions that we didn't have time to answer today. They will be addressed directly within the next few days by Tim. I'm going to leave you with our upcoming demo series topics. On October 24th, we will see a demonstration on managing commercial parts with component engineering. Then on November 7th, we will hear more on configurable permissions for effectivity on release bomb structures. You can register for upcoming demos and view any past demos at aras.com/demo-series. We'd love for you to join the Aras community at community.aras.com. There you'll find blogs, community projects, and forums, all with a lot of great information. Be sure to connect with Aras on LinkedIn, Twitter, and Facebook, where we share the latest updates and news, product information, and more. Finally, don't miss ACE Europe this November. We'd love to see you there to answer your questions, get your feedback, and take the opportunity to network with the PLM community, the Aras team, our partners, and more. We thank you for joining us today and look forward to having you visit us next time. Thank you and have a great day.